Solubility equilibrium. And another equilibrium that happens when we have things that are not completely soluble in solution. I think that's what it says right here on top. Now, you might recall from Gen Chem 1 when we had discussions about things that were saturated solutions and unsaturated solutions. You all remember that? Those topics? And if any of you have ever had upset stomach, do you ever take milk of magnesia? Anyway, all milk of magnesia is magnesium hydroxide that is not completely soluble in water. It's magnesium hydroxide, okay? Now, it is a group 2 metal hydroxide, so it is a strong electrolyte, as you've been learning. But if you look at the solubility guidelines, it's not 100% soluble under standard laboratory conditions. So if we were to write the equilibrium expression for that, we show, just like we do for a weak acid, well, of course, weak acid is always an aqueous solution, but it's not fully dissociated. All right. In this case, the magnesium hydroxide is only partially dissociated into its component ions. So we have solid and the product side, and then we have the 2 ions that it dissociates into an aqueous solution, when it does. And just like any equilibrium, we can write a mass action expression for that, which is the KEQ. At equilibrium, we're going to have the concentration of the products raised to their stoichiometric coefficients. So that's the magnesium 2 plus cation raised to the first power. And then we're going to have that multiplied by the concentration of hydroxide ions, in this case squared, because we have a coefficient of 2 here. So that comes here. This is nothing new, folks. Okay? And then divided by nothing. Because just like we found with the weak acids, right? These are all heterogeneous solutions, meaning that we have different phases. And in our mass action expression, we're only concerned about the things that are changing. All right? So if I have a glass of milk of magnesia here, and here's some solid magnesium hydroxide, okay? There's some little amount where the magnesium ions will come out of solution. And here, let's do this stoichiometrically. Let's do 2 hydroxide ions. Okay, but it's in equilibrium. It's a dynamic equilibrium. So as much that comes out into aqueous solution, the same amount reprecipitates back into the solid. Now that's the dynamic equilibrium, okay? But as far as the solid, as long as there's some solid in here, and this is exactly what it says right here, as long as there's some solid present, the system will be at equilibrium. And it doesn't matter how much solid there is. As long as there's some solid, it will be in equilibrium. And we don't include the solid in our mass action expression because the concentration of it doesn't change. In this case, what's the concentration of a solid? How would you measure the concentration of a solid? What would it be?
Density.
It's density, that's right. Because concentration is some mass or some amount per some volume. And that's what density is. And as you learned all the way back in chapter 1 of Gen Chem, the density of a solid is the same regardless of how much of that solid you're measuring. All right? It's the same argument that we had with water and why H2O was into the mass action expression. The concentration of water, the molarity of it actually, is the same regardless of how much water that you have. Or you can use that as a density argument as well. So we don't include that. I would write it here for you and say don't put it in your notes because I'm going to cross it out. So I'm going to save us that trouble. So that gives us then the KEQ for this special kind of reaction. So just like with acids, we called the KEQ the Ka, and with bases, we called it the Kb. With this, we're calling it the KSP. This is the solubility product. Solubility product. And it's just as the name describes. It's the product, right? You multiply things together of the things that are soluble. So that's going to give us then what we call the molar solubility. How many moles of the material will dissociate and be soluble? That's what molar solubility is. And we can calculate that directly from the equilibrium expression, as the bullet point here says. But let me show that to you mathematically. So let me just be specific here. This is of a saturated solution. How many moles are soluble but it has to be saturated, meaning that you have to have some solid there. If there's no solid present, you don't know if the solution is saturated or not. So we can build a rice table, will tell us this. Let's see. Let's build a rice table. So here's our magnesium hydroxide, and that's solid, and that's going to be in equilibrium with the magnesium 2 plus ion in aqueous solution plus 2 times the hydroxide ion in aqueous solution. Okay? And actually, before we continue with this rice table, let me show you one other thing here I forgot to mention. Look at this KSP. That's the value. Let's set that equal to the mass action expression that it represents. Okay? That's equal to, I have it written up above, but let's just be redundant here. The concentration of magnesium ions times the concentration of hydroxide ions squared. Okay? All right, now let's work on our rice table. So for the initial concentration, and we're not told what that initial concentration is, but whatever it is, we don't care, right? Per this discussion, the concentration never changes. So when I go and finish through this whole rice table, the concentration doesn't factor in of the solid because it stays constant. But we know that initially we don't have anything that's dissociated yet. So we know that some part of that solid is going to dissociate into ions. We're going to call that X, and we're going to subtract it from the solid, but the concentration of the solid is still the same. So that's never going to factor in, but I'll just put, we're subtracting that X from here, and the change is we're gaining X here, and what are we gaining for the hydroxide ion? 2X. That's right. So finally, at equilibrium, there's still going to be nothing here, and we're going to have X molar for magnesium ion and 2X molar for hydroxide ion. Okay? So let's now fill that in. Let's plug those values in. So that's going to be magnesium ion is X times, and then we have 2X for hydroxide ion squared. All right, so let's solve that. So 2x as a quantity squared is 4x squared, right? Here, let me not skip any steps. That's the same as x times 4x squared, which is equal to 4x cubed. You'll see what I did? So we can actually go back and solve for x now, can't we? This is kind of like one of the quiz problems that you had with pH. Right? You're given the Ka. In this case, it's the KSP. We can now solve algebraically. Right? We have an expression. 4x cubed is equal to 5.6 times 10 to the minus 12th. Sorry. So if we solve for x, we'll know what these concentrations are, and therefore we'll know how much was soluble. That's basically how you solve these. So let's go ahead and do that. Let's solve for x. So if 4x cubed is equal to 5.6 times 10 to the minus 12th, then we have x cubed is equal to 5.6 times 10 to the minus 12th divided by 4, and x is equal to the cube root of all of that. So that's 5.6 times 10 to the minus 12th divided by 4. The cube root, that's same as raising it to the exponent of the inverse. So that's raised to the 1/3 power. And all of you with calculators will tell me what that answer is. That's what x equals. Is that what my notes say? Yes. When X molar went into solution, it will dissociate completely into 1X of magnesium ions and 2X of hydroxide ions. But the molar solubility, how much is soluble, that is what X is. So we've got 1.12 times 10 to the minus fourth molar magnesium hydroxide is soluble. That's what molar solubility is. That's what we just solved for. All right, well, we'll practice with that a little bit, but first let's go back now and overlay some stuff that we learned earlier, like common ion effect and Le Chatelier's principle, to see how these other factors will affect the solubility of these materials. And so the first thing we'll look at is the common ion effect. So here's another material, barium sulfate, that is only partially soluble. And here is a similar mass action expression, except now if I were to build a rice table for this, once again, these concentrations aren't changing. And we start with 0 molar, we start with 0 molar, but some X is going to dissociate, okay? And when it does, it splits into equal parts now, X of barium ions and X of sulfate ions. And so at equilibrium, we're going to have X molar of that and X molar of that. Now, the published KSP for barium sulfate is 1.1 times 10 to the minus 10th. So it's really tiny. So just like as you evaluate KEQs, what does that tell you about the extent of this reaction? Does a lot of this become solubilized or just a little tiny bit? Very, very little bit dissociates because this number only represents the product of the ions that are solubilized, okay, which is not a lot. So we don't expect a lot to be solubilized here. But if we wanted to figure out what the molar solubility is, just like we did before, we need to figure out what X is, right? How much of this dissociated? How much of this is soluble? You want to try to figure it out? Figure it out. The KSP is just equal to X squared, right? So you just take the square root of that. You don't even need a calculator for this, depending on what if you have multiple choice, and what the answers are. It should be a little more than 1 times 10 to the minus fifth, right? 1.05 times 10 to the minus fifth is equal to X. That's the molar solubility. That's what this X is here. When it was solubilized, right, barium sulfate, that's going to then dissociate into its 2 ions, and those are 1 to 1. So this is the molar solubility when there's nothing in the water. We haven't done anything yet, okay? But now let's add a common ion, and let's see what happens. So we're going to take some sodium sulfate, and we're going to dump that into the solution. Now, sodium sulfate is not only soluble, it's also a strong electrolyte, right? Sodium ions as the cation. That's going to be a strong electrolyte. So let's, you're not told how much, so let's add, my notes say we're going to add 0.030 molar sodium sulfate into this solution. And we're going to see what effect it has. Now this is an arrow that goes to completion. So if I have initially 0.030 molar of sodium sulfate, and at that instant, before anything happens, we've got 0 molar and 0 molar. But then this is a strong electrolyte, so all of it's going to dissociate, and what do we have? What's the concentration of sodium ions going to be?
0.030 times 2.
Times 2, which is?
0.060.
0.060 molar, because we have twice as many sodium ions per mole of sodium sulfate. And what's the concentration of sulfate?
0.030.
0.030 molar. Now, which one is a common ion to the barium sulfate reaction? The sodium or the sulfate?
Sulfate.
It's not a trick question.
Sulfate.
Sulfate. So, we're going to take this and we're going to add it to whatever's going on up here. So So to do that, we need to build another Rice table. Because now we've got an equilibrium on top. But now we're disturbing that equilibrium, right? Common ion effect. It's Le Chatelier's principle, all right? So let's go and prove that. So just for completeness, I'm going to rewrite this the barium sulfate reaction down here so I can show you a nice, neat Rice table. Okay, and once again, initial now. So we don't have any barium here initially. So in either condition, so there's 0 molar barium ions. How many sulfate ions, or what's the concentration of sulfite ions at the initial step before we add, before the barium sulfate dissociates? What's the concentration of sulfate ions? 0.03 now, because we've added the sodium sulfate. So that's the difference here. Now the change, do you need to evaluate Q versus KEQ and see which direction it's going to shift? You've got a 0, so you know it's going to go in the right hand. You know it's going to go towards products. If we had concentrations for both of these, you wouldn't know, and you'd have to calculate Q and evaluate that to KEQ and all that stuff. But here we know it's going to go to the right, so we're going to lose some X from this, and we're going to gain X here, and we're going to gain X here, because it is 1 to 1. Okay? So at equilibrium now, we've got X molar for barium ion concentration, and we have 0.030 plus X for the sulfate ion concentration. Now we need to solve for the molar solubility just the same way we did before. We need to solve for X. Now KSP hasn't changed. All right? So let's write this in now. 1.1 times 10 to the minus 10th. That's our KSP. That's equal to, now it's no longer just X squared. Now it's X for the barium ion, and it's 0.03 plus X for the sulfate ion. Now you can multiply this through, and it becomes a quadratic that you have to solve for the quadratic formula, which we're not going to do. Okay? But keep in mind that we already discussed that the solubility product is so small that very, very little dissociates. So even with or without a common ion, we don't expect X to be very, very large. In fact, we already know that when there's no common ion there, X is pretty small. It's 10 to the minus 10th. It's basically, oh wait, that was X squared, sorry. 10 to the minus 5th. That's still pretty small. But importantly, it's negligible compared to 0.03. All right? This number is 0.00001 versus 0.03. So if we subtract X from this, we're still pretty much going to get 0.03. So we can ignore this X, and it makes the whole thing much simpler. Because now we have 1.1 times 10 to the minus 10th is equal to 0.03x. So x is now equal to 1.1 times 10 to the minus 10th divided by 0.03, which is equal to 4 times, looks like 10 to the minus 9. Now this represents the new molar solubility. Now before we look at the numbers, just look at Le Chatelier's principle. What are we doing here? Here's our equilibrium. Everything was happy, okay? And then we upset that equilibrium by adding more sulfate. So what do you expect is going to happen here? Which way is this equilibrium going to shift to reach a new equilibrium given that we're adding sulfate ions? Is it going to go this way or is it going to go this way? Think about what we're doing. We're adding 0.03 molar to this. So this is going up. So what's going to happen to the equilibrium? It's going to shift to the left. It's going to shift this way. That's what we expect, which means what's going to happen? What do we expect to happen to the molar solubility? Is it going to get higher or lower? It's It's going to get lower. We're forcing more back into the solid by adding the common ion. Okay, so we have a feel that the reaction is going to shift back to the left. Do the numbers support that? Here's the original molar solubility, and here's the new molar solubility. So what do you think? Is that consistent or inconsistent with our expectation? This number says we have basically 10 to the minus 5th molar. This shows that we now have 10 to the minus 9th molar that's solubilized. So that's consistent. By adding the common ion, we're shifting this reaction towards more solid, so we expect less of it to be soluble. Here is the same idea looking at it with respect to pH. Since we just got finished talking so much about pH, let's do the same thing here. Now let's look at the effect of the pH on the solution. And what's that going to do to our molar solubility? So here's some calcium fluoride. All right, and here's the mass action expression for calcium fluoride. Now let's go ahead. Here's the KSP that I looked up in the back of the textbook. Shall we solve for the molar solubility?
Yes.
Calcium fluoride? Yes. Go ahead and do it. All right, I'm going to go ahead. All right. Just like we did before. All right. We build our rice table. We show our mass action expression, and then we plug the values into our mass action expression. So that means that this KSP is going to be equal to, this is X, and the F minus, that's 2M, or 2X, right? So this is going to be 2X squared, which means this whole thing is equal, once again, to 4X cubed. 5.3 times 10 to the minus 9th is equal to 4X cubed. So it's the same as we had before. Okay? And yeah, start looking at patterns. Here we have a ionic compound that when it dissociates into 3 components like this, with a 1:2 ratio. That will give you 4x cubed when you set this up, always. So you do the math, you solve for x,
Times 10 to the minus 3.
and you can put that in scientific notation. That's perfectly fine. 1.1 times 10 to the minus 3rd molar. Both of those are perfectly acceptable, right? That's the molar solubility. Now that's when it's in pure water. But now let's add some acid to it. See what happens. Now in this case, it's not just any old acid, right? We're going to be doing this by the common ion effect. If we take hydrogen fluoride, well, we're not going to take it, right? Actually, this is true for any acid. I take that back. This is true for any acid. Any acid that you add to this solution is going to basically add hydronium ion to our reaction. So you can add sulfuric acid, carbonic acid, nitric acid, it doesn't matter. The acid, the definition of an acid is that we are donating protons to the solution. Okay, so when we add the hydronium ion, here it is. This is what's added to the solution. But what's already in the solution? We have fluoride ions. And we recognize our conjugate pairs, all right? Fluoride is the conjugate base of a weak acid. It's the conjugate base of hydrofluoric acid. Okay? So it's weak, meaning that it's all the Chatelier's principle again. We're adding acid, so what's going to happen to this? It's going to shift this way. We're adding more reactant, so it's going to shift this way. So when we shift that way, what are we doing to the fluoride ion concentration? It reduces. Which is going to affect that up there. So now we're reducing. If this gets reduced, which way is it going to shift to establish a new equilibrium? It's going to go this way. Which means that we had stuff that was soluble, we had stuff that was solid, and now it's going to become more soluble. So calcium fluoride will become more soluble in acidic solution. And we don't need to put numbers to this one. Right? We did enough computation with the previous example. I expect you to be able to think about these things both empirically or qualitatively, is a better term for this, right? Just like we've described. What's going to happen? Is it going to become more soluble or less soluble? But let me spend a little bit of time here now just showing you these patterns. Because we've seen some of them already more than once. The 4x cubed. You're only going to see so many varieties of these because there's only so many combinations of anions and cations in ionic compounds, whether they're soluble or not. Now we're considering this is KSP, so everything's going to be a solid. Here with A and B, so A is the cation, and B is the anion. As we always do, our convention is cation first, anion second, and then you learn this in Gen Chem 1. What's the ratio of cations to anions to give you a net neutral compound? That's where you do the crisscross or the lowest common multiple or however you learned it. All right? And now we're going to consider what it looks like in the context of a Rice table and in making our KSP mass action expression. We're going to figure out the proportion of ions that it dissociates into. If it's just AB, we already did this one. That dissociates into X and X. So whatever the KSP is, it's going to be equal to X squared. And we did this next one a few times, AB2, right? When it dissociates into 1 mole of A and 2 moles of B. And so when we write the KSP for that, it's going to be equal to the concentration of A raised to the first power times the concentration of B raised to the second power. That's going to be X and 2X squared, which is equal to 4X cubed. And down below, it's the same thing. A2B, it dissociates into 2X and X. So the KSP is going to be the same, except now it's equal to 2X squared times X, which is still equal to 4X cubed. Doesn't matter. What are you going to get if it's one of these two? It's going to be the same answer, but what are you going to get? You figure it out. Are you sure it's 6 or is it 5? Let's figure it out. Let's do it together. All right, so A2B3 will break into 2X of A and 3X of B, and when we do the KSP for that, it's going to be the concentration of A raised to the second power times the concentration of B raised to the third power. That's going to be 2X raised to the second power times 3X raised to the third power. That's going to be 4X squared times 27. Thank you. 27. 3 cubed is 27. X cubed. And 27 times 4 is 108. And then that would be X to the 5th. Okay? That's how they work. There's only so many combinations. In fact, there's one more that I realized after I made this slide for you. There's other compounds, ionic compounds, that would take the form of AB3 or A3B. Right? But it's the same idea. We take this, it dissociates into 1 mole of A and 3 moles of B. So the KSP is going to be equal to, so this is going to be X, this is going to be 3X. So it's going to be A times B cubed. So that's going to be equal to X times 3X cubed, which is equal to 27 x cubed plus times x, right? So 27x to the fourth. And I believe these are the only combinations of these for solving for KSP that we have. Because it's all based on this principle, and these are the only kinds of ionic compounds that we're dealing with. So here, we're given the molar solubility. I'm just going to work it backwards. So the molar solubility is equal to 2.7 times 10 to the minus 7th molar. And we're asked to calculate the KSP. And what's the compound? It's lead carbonate. So write out, what does that dissociate into when it dissociates into its ions? We've got lead 2 plus in aqueous solution and the carbonate ion. Now, if you didn't know that it was lead 2 plus, you got to know your polyatomic ions, especially the common ones that we use all the time. Carbonate is a 2 minus. All right, so this is going to be an x and an x. So we know that KSP, all right, is equal to x squared. Now this is x. That's the x that dissociates from the solid before it splits into its ions. So now we know that KSP is equal to x squared. So KSP is simply equal to 2.7 times 10 to the minus 7th squared. And that should be the KSP. You look it up, it should be pretty close.